In the previous lecture, we proved that if f bar is an algebraic closure of the field f, then the extension f bar over f is a Galois extension, precisely when f is a perfect field. Now that we have a Galois extension, we can ask ourselves how much Galois correspondence theorem between the intermediate subfields of f bar over f and subgroups of the group of automorphisms of f bar hold in this infinite dimensional case as well. So if you remember in our case, in the case that we discussed the fundamental theorem of Galva theory, we only discussed the case when E over F is a finite Galva extension. F bar over F is of infinite dimension. So that is the question that we want to understand. We can still define the functions that we had in the fundamental theorem of Galva theory, meaning we have the function psi from the set of intermediate subfields of f bar over f to the set of subgroups of the group of automorphisms of f bar, f linear automorphisms of f bar, meaning I give you an intermediate subfield and you give me back E linear automorphisms of the field f bar. So that would be a subgroup of f linear automorphisms of f bar. Or I can take a subgroup of f linear automorphisms of f bar and simply take the fixed points of this subgroup. And we've proved that fixed points of any subgroup of group of automorphisms gives me back an intermediate subfield. So these functions are still well-defined functions in this infinite dimensional case as well. One of the key results that we proved in finite dimension was that the fixed points of the E automorphisms of f bar, or so if L over K is a Galois extension of finite dimension, then the fixed points of K automorphisms of L is precisely K. This was one of the key results that we proved. And if you think about it, this exactly means that phi O psi of E is E. So this equality tells us that at least, okay, so when we want to say phi and psi are inverse of each other, we have to show psi O phi and phi O psi, both of them are identity. This proposition tells us that at least one of these identities hold. So it says that phi of psi is always the identity map. So the fixed point of E automorphisms of f bar is precisely E. Okay, let's see how the proof goes. What is clear is that the set E, because I mean, by definition, E automorphisms of f bar, when I restrict them to E, I get identity. These are E linear maps, so an element over E is sent to itself. So definitely E is fixed under every E linear automorphism of f bar. So this means that we clearly have that E is a subset, E is a subfield of the fixed points of E linear automorphisms of f bar. Now we want to show the other way around. We want to show that the fixed points of E automorphism of f bar is precisely E. We assume to the contrary that there is an element alpha that is fixed by all E automorphisms of f bar, but it's not inside E. Notice that every element in f bar is algebraic over f. E contains f, so every element in f bar is algebraic over E. Now, because alpha does not belong to E, the minimal polynomial of alpha over E should have degree at least 2. So it is algebraic. We can't talk about the minimal polynomial of alpha over E, and it's not inside E, so the degree of the minimal polynomial should be at least 2. Now, that means when I split the minimal polynomial completely, I have at least 2 zeros. Okay, so let's break this down into 2 steps. So the first thing is that the minimal polynomial of alpha over E can be written as a product of degree 1 factors over F bar, because F bar is algebraically closed. Second, because F bar over F is a separable extension, F bar over E is also a separable extension, and that means minimal polynomials cannot have multiple roots. Degree of the minimal polynomial of alpha over E is at least 2. This means it does have a different zero, another zero, which is different from alpha. So let's pick one of those zeros. So suppose alpha prime in this algebraic closure is another zero of the minimal polynomial of alpha over E. So alpha prime is a zero of the minimal polynomial of alpha over E, and alpha prime is not alpha. Notice that the minimal polynomial of alpha over E is an irreducible polynomial, and I'm giving you 2 zeros of this. We have shown this long ago, then therefore there is an E isomorphism from E bracket alpha after joining alpha and after joining alpha prime. So there is an E isomorphism that sends alpha to alpha prime. If you think about it, I mean, let me quickly recall how the proof goes. The point was that E bracket alpha is isomorphic to the quotient of E bracket x by the ideal generated by the minimal polynomial. The same is true for E bracket alpha prime, because alpha prime shares the minimal polynomial with alpha. Both of them are zeros of the irreducible monic polynomial m sub alpha comma E. So they share minimal polynomials, therefore we are getting the same quotient of the ring of polynomials of E bracket x. And if you look at the isomorphism between E bracket alpha and the quotient of the ring of polynomials, the isomorphism comes from the evaluation. One of them substituting alpha for x, the other one substituting alpha prime for x. So this, if I follow the arrows correctly, we get an E isomorphism between E joint alpha and E joint alpha prime, which sends alpha to alpha prime. Okay, so that was a quick recall on how the proof of this statement goes. Now, the next thing that we notice is that F bar is algebraic over F, and therefore it's algebraic over every intermediate subfield, including E bracket alpha and E bracket alpha prime. And F bar is algebraically closed. That means F bar is an algebraic closure of both of these fields. It's an algebraic closure of E bracket alpha, and it is an algebraic closure of E bracket alpha prime. Now, the isomorphism extension theorem that we have provided, I mean, we have proved it for isomorphism extension between the same field F and to F, but the same argument works for any isomorphism between two fields and any algebraic closure of those fields. Therefore, by the isomorphism extension theorem for algebraic closures, we can extend this theta to an isomorphism between F bar and F bar. Remember, F bar is an algebraic closure of both of these fields, so I can extend the isomorphism between these fields to an isomorphism from F bar to F bar. So let's say theta hat is this extension of theta. That means that theta hat is an isomorphism from F bar to F bar, and theta hat restricted to E bracket alpha is theta. In particular, when I restrict it further down to E, because theta is an E-linear map, we deduce that theta hat is E-linear map, because the restriction to E would be the restriction of theta to E, but restriction of theta to E is identity, because theta is an E isomorphism. So theta hat is E automorphism of F bar, and theta hat applied to alpha is the same as theta applied to alpha, but theta applied to alpha is alpha prime. So theta hat of alpha is alpha prime. So we end up finding an E-automorphism of F bar which sends alpha to alpha prime. That means alpha is not fixed under this group. Alpha does not belong, is not in the fixed points of E-automorphisms of F bar. That's a contradiction because we chose alpha to be inside this set. We get a contradiction, and that completes the proof of this proposition. Now let's think about it, what it says. We are starting from the intermediate subfields of F bar over F. We apply psi, we get a subset of subgroups of F automorphisms of F bar. And when I apply phi, I get back what I started with. So phi of psi is identity. That means psi is injective and phi is surjective. I might not get all the subgroups of F linear automorphism of F bar. I might get only some fraction of it or some part of it. But if I restrict my attention to only these subgroups that I gain through psi, if I focus only on the image of psi, then phi and psi would be inverse of each other. So phi and psi are inverse of each other if I think about them as functions from the intermediate subfields of F bar over F to image of psi. What is image of psi? Elements in the image of psi look like this. Those subgroups that are E automorphisms of F bar for some intermediate subfield E. So if I focus only on these subgroups, then phi and psi are going to be inverse of each other. One can put a topology on the group of F linear automorphisms of F bar. This topology is not going to be interesting. I mean, one can do this for any Galva extension, and this topology for finite dimensional Galva extensions would not be interesting because all the subsets would be open sets. We call such a topology discrete topology. But when the extension is not a finite extension, then it's a rather interesting topology. It's called the cruel topology of the Galva group. And with respect to this topology, the image of psi is precisely the set of closed subgroups of F linear automorphisms of F bar. So closed subgroups of F linear automorphisms of F bar would be this set. We are not going to discuss the cruel topology of the F linear automorphisms of F bar, but we are going to refer to the set, to the image of psi as the set of closed subgroups of F linear automorphisms of F bar. So what we just showed shows that there is a bijection between the closed subgroups of F linear automorphisms of F bar and intermediate subfields of F bar over F. Now, similar to Galois' fundamental theorem of Galva theory, we have a second part, meaning we want to understand the bijection between normal extensions and normal subgroups. And the claim is that if I restrict myself to closed normal subgroups, then we get a bijection. So claim is that psi and phi induce bijections between intermediate subfields where E over the base field capital F is a normal extension, and subgroups of F linear automorphisms of F bar that are closed and normal. So there is a bijection between closed normal subgroups of F linear automorphisms of F bar and normal extensions, intermediate subfields of F bar over F that are normal over the base field, capital F. Moreover, if E over F is a normal extension, then the group of F linear automorphisms of E, you see, so whenever you are working with automorphisms that are F linear, F is your base, then you have to use the restriction map, and that would be F linear automorphisms of the top mod out by E linear automorphisms of the top. Then we get this isomorphism. This isomorphism we have essentially discussed in the previous lecture, but we are going to go over that argument again. Okay, let's start with showing that if E over F is a normal extension, then did we call it psi? Yes, then psi of E is going to be a normal subgroup of the F linear automorphisms of F bar. So suppose E over F is a normal extension. Psi of E would be E linear automorphisms of F bar, and we want to say that it's a normal subgroup of F linear automorphisms of F bar. In fact, we show this simultaneously with this isomorphism. How do we do it? We have already discussed that because E over F is a normal extension, the restriction map is a well-defined group homomorphism. It's a well-defined group homomorphism because every alpha that I give you in E, when I apply theta, and I give you theta inside the F linear automorphisms of F bar, I give you alpha inside E, then theta of alpha should be another zero of the minimal polynomial of alpha over F. But E over F is a normal extension, so that means that all the other zeros are already inside E. So alternatively, I should say that the minimal polynomial of alpha over F can be written as product of linear factors in E bracket X. So theta of alpha is also inside E. That means that the restriction map is indeed a well-defined group homomorphism. And we have already claimed that it is also surjective. Let's quickly say why this is the case. But before we get to the image of R sub E, let's discuss the kernel of R sub E. So when we say something is in the kernel, what does that mean? This means that when I restrict it to E, I get identity. That's the definition of getting an E linear automorphism of F bar. So this means that E linear automorphisms of F bar is precisely the kernel of the restriction map, and that implies that E linear automorphism of F bar is a normal subgroup of this, and clearly it is also a closed subgroup because it is in the image of psi. Okay, so having an intermediate subfield, we end up getting a normal closed subgroup of F linear automorphisms of F bar. Now let's also say why R sub E is surjective. So we pick an element inside E, F automorphisms of E. Now I view F bar as an algebraic closure of E, and I use the isomorphism extension theorem for algebraic closures, and I extend theta to an F linear automorphism of F bar. So we end up getting theta hat. That's an F linear automorphism of F bar. And that's the definition of saying that theta is R sub E, the restriction of theta hat, which means R sub E is a surjective map because theta was arbitrary. So the image of R sub E is the entire F linear automorphisms of E. The kernel is E linear automorphisms of F bar. So if I use the first isomorphism theorem, we get that the quotient of F linear automorphisms of F bar by the kernel of the restriction map, which is this, is isomorphic to the image of restriction map, which is the set, the group of F linear automorphisms of E. So we showed two of the claims. We showed that psi of E is a normal closed subgroup and we got the isomorphism out of it. Now we want to show the other way around. We start with a normal closed subgroup of F linear automorphisms of F bar, and we want to show that fixed points of that is indeed a normal extension over the base. In fact, in this direction, we are not going to use the fact that the normal subgroup is closed. This statement is going to be true even if n is not a closed subgroup. So suppose n is a normal subgroup, arbitrary normal subgroup of the group of F linear automorphisms of F bar, and we want to show that the set of fixed points of n give us a normal extension over the base field capital F. So fix n over F, the claim is that this is a normal extension. What does that mean? This means I give you an element inside fix n, and then I need to show that the minimal polynomial of alpha over F can be written as product of degree 1 factors with in fix n bracket x. So we need to decompose the minimal polynomial of alpha over F. We can do the decomposition in F bar because F bar is algebraically closed. So I start with the minimal polynomial of alpha over F, and then I find other zeros of this minimal polynomial in F bar. Because F bar is algebraically closed, I can do this. And I write down the minimal polynomial of alpha over F as product of x minus alpha 1, x minus alpha 2, x minus alpha n, and I choose the ordering in a way that, I mean, alpha should be one of these because it's a minimal polynomial of alpha over F, and I choose alpha 1 to be alpha. Okay, so these alpha i's are inside F bar. Now, for every I that you give me, there exists an F isomorphism between F isomorphism from F bracket alpha 1 to F bracket alpha I, because they share minimal polynomial. So there is this theta sub I, which is F linear from F bracket alpha 1, which is F bracket alpha, to F bracket alpha I. Now again, we notice that F bar is an algebraic closure of both F bracket alpha 1 and F bracket alpha I, because it's algebraically closed and it is algebraic over these intermediate subfields. So F bar is an algebraic closure of these fields, and so I can use the isomorphism extension theorem again, the isomorphism extension for algebraically closed fields. So using that result, I can extend this theta sub I to an isomorphism from F bar to itself. So I get these theta I hats from F bar to itself. You see, what we are showing is that the group of automorphisms of this huge field act transitively on the minimal polynomials of every element over the base field, capital F. We can send one of the zeros of these minimal polynomials to another one via an automorphism, a symmetry of this huge object. So we have a lot of symmetries. Okay, so so there are theta I hats from F bar to F bar, where the restriction of theta I hat is to F bracket alpha 1 is theta I here. Let me emphasize that this theta sub I sends alpha 1 to alpha I. So that is what I was referring to, that the action is transitive. It sends alpha 1 to any other zero. So in particular, when I restrict theta I hat to F, I get restriction of theta I to F, which is an F linear map. That means that theta I hat is an F linear automorphism of F bar. And theta I hat, when I restrict it to alpha 1, it's like the restriction of theta I to alpha 1. Theta I sends alpha 1 to alpha I. So theta I hat sends alpha 1 to alpha I. So that's exactly the transitivity that I was pointing out. But now notice that Okay, so now what do I want to show? My goal was to show that all the other zeros are still inside fix n. So my goal is to show that alpha I belongs to fix n. But what do I know? I found these theta I hat that sends alpha 1 to alpha I. I know alpha 1, which is alpha, is in fix n. And I know that n is a normal subgroup of the F linear automorphisms of F bar. So these are what I know, and this is what I want to show. Okay, let's again think about it. What do I want to show? I want to show that alpha I is fixed under n. So let's pick something inside n. So let's pick sigma from n, an arbitrary element, and I need to show that sigma of alpha I is alpha I. But what is alpha I? Alpha I is theta I hat of alpha 1. So I need to show that sigma of alpha I hat of sigma of theta I hat of alpha 1 is theta I hat of alpha 1. So this is what I need to show. Now I can manipulate it, or multiply both. So I apply the inverse of theta I hat to both sides. So this equality holds precisely when this one holds. Theta I hat inverse of sigma theta I hat applied to alpha 1 should be alpha 1. Okay, now think about it. This is conjugation of sigma by an element inside F linear automorphisms of F bar. N is a normal subgroup. Sigma is inside N. N is a normal subgroup. Sigma is inside N. Therefore, every conjugate of sigma is also inside N. In particular, theta I hat inverse of sigma of theta I hat is an element of N. This is inside N. Alpha 1 is in fix N. So every element of N fixes alpha 1. So we get 2. We get that this holds because this is an element inside N, and every element inside N fixes alpha 1. So we get that this 2 holds, and from there we can deduce that 1 holds, and that means that sigma of alpha I is alpha I, and that's true for everyone. That means for every sigma, that means that alpha 1. That means that alpha I is fixed in N, and that completes the proof. Okay. So altogether, we got that this psi and phi that we have, they give us a bijection between intermediate subfields of F bar over F and closed subgroups of F linear automorphisms of F bar. And this bijection sends normal extensions over the base field to normal closed subgroups of F linear automorphisms of F bar. Now, in Galva theory, we've seen that this understanding of this symmetry of F linear automorphisms is extremely crucial. And we've seen that many of the properties of field extensions have an external and internal interpretation. So for instance, when we were talking about normal extensions, one way was by saying every element inside, when I look at the minimal polynomial, it can be factored completely into linear into degree 1 factors. But then we could also think about it from outside and say that if I pick any tower on top of that, then when I pick an automorphism of this larger algebraic extension, then it sends this E to itself. So you see, when I give you an extension E over F, either I could go above that and take some algebraic extension of E and then use that to understand the extension E over F, or I could work with elements inside E. Okay, so either we had internal or external understanding of this. For perfect fields, it's the same. So a field is perfect. Either we can describe it completely in terms of the field itself, F. Either it's the characteristic is 0, or F to the P is F, where P is the characteristic of F. Or I can say that every algebraic extension of F is separable. So either internal or external. There is always this kind of a dichotomy between properties that we see. Now here we want to see how much of this kind of external internal properties we can see in the symmetries of F bar over F. So this is a group. F bar over F is a group. Now we can ask ourselves, okay, so if I give you a group theoretic property of this extension, what does it tell me about the extension itself? Or if I give you a collection of subgroups of this, what kind of properties does it give me about in terms of the intermediate subfields, and do I have an interpretation, internal interpretation of these extensions? Okay, so let's make it concrete. Let's look at finite cyclic quotients of F bar over F. So I want to understand F bar over F as a group. It's important for me because we understood that symmetries of this extension can give us a lot of information about the extension itself. And this extension is quite rich because every other algebraic extension of F can be embedded inside this extension. We want to understand the extension of bar over F. Inspired by Galva theory, we want to understand the group of F linear automorphisms of F bar. I want to understand this group. Can I understand finite cyclic quotients of this group? And we've learned, because of the bijection that we showed, it's better to focus on closed subgroups. So we want to understand finite cyclic quotients of this group by its closed subgroups. If we manage to do that, next level would be, what can I say about finite abelian quotients of this group by closed subgroups? Let's start with finite cyclic quotients, but along the way we try to see how much we can relax this condition that it's a cyclic extension, cyclic subgroup. Again, when we say closed subgroup, that means that it is of the form E linear automorphisms of F bar. For some E, that's an intermediate subfield, and we proved that when I want to work with a normal subgroup, then I need to work with a normal extension. So when I talk about a quotient of F linear automorphisms of F bar by a closed subgroup, by the theorem, by the proposition that we proved, we are given a normal extension of F. And because I'm asked to, we want to understand finite cyclic extensions, and we proved that the quotient of F linear automorphisms of F bar by E linear automorphisms of F bar is isomorphic to F linear automorphisms of F bar, of E, and because we are assuming that this quotient is a finite group, this means that E over F is a finite normal extension, and we are assuming that this quotient is supposed to be cyclic. This means that we want to understand cyclic normal extensions, cyclic finite normal extensions of the base field F. That's the question that we want to understand if it has an internal counterpart. So we are given this base field F, and we want to understand if we can formulate an internal counterpart for finite cyclic extensions or abelian extensions of the base field F. And in order to make it, this is quite, I mean, so theoretically I have to say where E is ranging, E is an intermediate subfield of this algebraic closure F bar. Okay, so that's the question that we want to understand. We want to understand if there is a, what is the internal counterpart of finite cyclic or abelian, or finite cyclic or abelian extensions of E over F. E over F, where E is an intermediate subfield of F bar over F. Okay, so it's a finite cyclic group. Let's say assume that this is a finite cyclic group of order n. This is the quotient that we wanted. And as we have discussed here, we are assuming that F is perfect field. In fact, let's assume that the characteristic is 0 to avoid, to make sure that every extension is separable and we don't need to be worried about separability issues. So characteristic is 0, and I'm working with a cyclic extension of the base field. By Coomer, we know that if the base field has enough roots of unity, then we have a fairly good understanding of this extension. We showed this in the context of radical extensions when we wanted to show, when we wanted to understand the chain of radical extensions, we added enough roots of unity in order to use this result due to Coomer, that if F contains an element whose multiplicative order is the same as the degree of the field extension E over F, then E over F is a Coomer extension. That means what? That means that E is F joint with nth root of A for some A inside F. And nth root of A is a symbol that I'm using to denote, it's not a canonical symbol, it's one of the zeros of x to the n minus A inside this fixed algebraic closure. Notice that in F bar, x to the n minus A has n distinct zeros. One of them is the nth root of A. The other ones are zeta to power I times the same number, the same element. We have discussed that this Coomer extension is indeed a splitting field of x to the n minus A over the base field capital F, and therefore this extension is a normal extension. The characteristic is 0. From there, we can deduce that this extension is indeed a Galois extension, and we proved that the Galva group of this extension is cyclic. And in fact, we showed that it is not only cyclic, but also can be embedded inside Z mod NZ. So these are the things that we have proved based on ideas due to Coomer. Now, as part of Coomer theory, we get a complete understanding of internal interpretation of cyclic extensions of base field F when F is of characteristic 0 and has enough roots of unity. What do I mean by that? Here is the precise formulation. Suppose F is a field, characteristic is 0, and it does have a root of unity whose multiplicative order is n. In that case, we can understand cyclic extensions, intermediate subfields that are cyclic extensions over the base field, and they can be embedded into Z mod n. So let's define, let's give a notation for these set of intermediate subfields. So let int sub Zn of F bar over F be the set of intermediate subfields of F bar over F, so that E over F is a Galois extension, and the F linear automorphisms of E can be embedded into Z sub n. In particular, it's a cyclic extension, and the cardinality of this extension, the degree of this extension, divides n. So that's an alternative way of saying it. So on one hand, we have this. On the other hand, we have, now I want to give you an internal counterpart. So you look at F cross and mod out by f cross to the n. So that's completely in terms of f. We don't go outside of f. We are not working with field extensions. I'm giving you f, and I'm working with elements inside f. So I look at the non-zero elements of f, mod out by, I raise all of them to power n, I get a subgroup, and I'm modding out this abelian quotient, this abelian group by this quotient. So I get, this is the largest quotient of f cross that is n torsion. Every element raised to power n is identity. Now inside this group, I look at the set of all the subgroups that are cyclic. So I'm looking at cyclic subgroups of f cross over f cross to the n. And because these guys are n torsion, they all can be embedded into z sub n. So these are cyclic subgroups of f cross over f cross to the n. So they consist of groups. I mean, this set consists of those groups that are generated by some element inside this f cross over f cross to the n. Now, the claim is that there is a natural bijection between these intermediate subfields that are giving me cyclic extensions that can be embedded into z sub n and cyclic subgroups of f cross over f cross to the n. Okay, what is this? What are these natural bijections? I need to give you a map. This map takes a cyclic subgroup and gives me an intermediate subfield. Let's denote this map by lambda. So what is lambda of the cyclic group generated by the coset that's represented by A? Lambda of the coset represented by A, the group generated by the coset that's represented by A, is nothing but adding a root of x to the n minus a to the base field f. That's lambda. Of course, I need to justify this notation because I can choose a different generator, and I can choose a different 0 for x to the n minus a, and I need to justify why both of these are okay. So if I choose a different generator, what happens? If I choose a different 0, what happens? I need to say that in either case, I'm not changing this field. Now, the other way around, I give you an intermediate subfield, let's say it's E, with this property that E over F is Galois, and the Galva group can be embedded into Z sub n. Now, having this field, what is the subgroup? I raise all the non-zero elements of this field, raise them to power n, and then ask myself, am I getting an element inside F? So essentially, I'm asking myself, what are the elements inside this field that are zeros of some polynomial of the form x to the n minus a for some a inside F? If I have such a 0, I put it inside this group. Notice that this is intersection of two groups, then definitely it's a group. And this group definitely contains f cross to the n, because if I start with something inside f cross and raise it to power n, it is already here, and it is also inside here. So it does contain f cross to the n, and then I mod out this group by the other one, and I'm getting a subgroup of f cross mod out by f cross to the n. What is not clear is why this group is cyclic. But that's our claim, that this is indeed a cyclic subgroup of f cross over f cross to the n, and I denote this by delta of E. So now I've not defined, but I've claimed that I can define these two functions, lambda and delta, and I need to prove why either of them are well-defined functions. It's not clear at all why these are well-defined functions. But the claim is that not only they are well-defined functions, but also they are inverse of each other. So it's quite a strong statement. Furthermore, the group generated by the coset represented by A, that cyclic group, is isomorphic with the Galva group of the extension that we get through lambda. So I give you this cyclic group. The cyclic group is isomorphic to applying lambda to this cyclic group and then looking at the F-linear automorphisms of this. Or I give you this intermediate subfield with cyclic Galva extension and the cardinality of this, the degree of the extension divides n. Then the Galva group of this extension is isomorphic to the group that we get out of delta. So it's a quite interesting theorem that gives us internal interpretation about cyclic extensions, finite cyclic extensions of a field with enough roots of unity. And this bijection also detects the Galva group of the extensions via these internal interpretation. Okay, let's see how the proof goes. Before getting to the proof of this statement, we are going to start with what's called Coomer pairing. This Coomer pairing is essential for the abelian setting as well. So I will start with discussing this Coomer pairing even without assuming that the extension of E over F is an abelian extension. But it's not going to be strong unless the extension is an abelian extension. In fact, it's only give us information about abelian quotient of F-linear automorphisms of E. But we start with a general discussion, then later on we will restrict ourselves to cyclic or abelian cases. But the idea is what you have already seen earlier in your homework assignments. And when we wanted to show that Coomer extensions are indeed cyclic extensions and the Galva group of them can be embedded into Z sub n. So how did we show such thing? We took the nth root of A. We said that this is a 0 of x to the n minus a. Then we took an element inside the F-linear automorphisms of E. We said when we apply this sigma to the nth root of A, it should give me another 0 of x to the n minus a. Then we discussed that x to the n minus a, all the zeros of the form zeta to power I times nth root of A. Then that means sigma of the nth root of A is zeta to some power times nth root of A. And essentially we work with that power of zeta. Okay, let's go through the argument again, but in the language of Coomer pairing. So we are given an element inside F linear automorphisms of E. So the assumption, the standing assumption is that E over F is some field extension, and delta of E is this. That's my delta of E, and E over F is some field extension, and we'll see what we can do with it. So I give you an element inside delta of E, and I give you an element inside F linear automorphisms of E. Now, this F, having this pair of elements, is supposed to give me an nth root of unity. Okay, so notice that because zeta has multiplicative over n, then the group generated by zeta has n elements, and it's a cyclic group, and in fact, it contains all the elements that are solutions of x to the n minus 1. These are all the nth roots of unity inside the field F. And we are going to denote this by n sub n. Now, given sigma, and given an element here, so what does that mean? That it's an element here. An element over here is something inside E raised to power n that happens to be inside F cross. So it's something inside E, that's what we call alpha, raised to power n, and then we look at the coset represented by that, and by assumption, this guy belongs to F. So that's our assumption, that alpha to the n belongs to F. Now, given such alpha, we take the coset, and then this F takes this pair of sigma and this coset, and it spits out sigma applied to alpha divided by alpha. Now, what is not clear are two things. What are not clear are two things. So what is not clear is that why this definition does not depend on the choice of coset representative. So what happens if I choose another coset representative? So if I tell you alpha 1 to the n and alpha 2 to the n, both of them are giving me the same cosets, then do I get the same quality? The other thing that's not clear is why this quotient is in fact inside m sub n. Why is it an nth root of unity? So I need to address both of these issues. Okay, let's start with why this function f is indeed a well-defined function. Let's start by saying why sigma of alpha over alpha is indeed an nth root of unity. Okay, what do I know about sigma of alpha? What do I know about alpha? Alpha, if you remember, alpha was chosen in a way that alpha raised to power n is inside f. So alpha raised to power n is supposed to be an element inside f, and alpha is a non-zero element of E. So let's denote alpha to the n by a. So a is an element of f. That means alpha is a zero of x to the n minus a. We have seen this type of argument many times, that when alpha is a zero of this and zeta is an nth root of unity, then alpha, zeta of alpha, zeta to power n minus 1 times alpha, these are going to be all distinct zeros of x to the n minus a. Then one can use the generalized factor theorem, then compare the degrees, compare the leading coefficients, and deduce that x to the n minus a is x minus alpha, x minus zeta of alpha, x minus zeta squared alpha, till we get to the last term, which is x minus zeta to power n minus 1 alpha. So we get a complete factorization of x to the n minus a, and now we notice that no matter what sigma is, sigma of alpha should be another zero of this binomial. Sigma permutes zeros of binomials in f bracket x. So sigma permutes zeros of this, zeros of x to the n minus 1, x to the n minus a, and that means that sigma of alpha is of the form zeta to power I times alpha, which means the fraction sigma of alpha over alpha is indeed inside the cyclic group generated by zeta. Okay, so far good, so good. So if we show that it's independent of the coset representatives, that implies that this pairing is at least well defined. Now, let's pick two different coset representatives that give me the same coset. So suppose that alpha 1 raised to power n, the coset that we get out of this is the same as alpha 2 raised to power n, the coset that we get out of that. And again, the assumption is that alpha 1 to the n and alpha 2 to the n, both of them belong to f. When we say that these cosets are the same, that means that alpha 1 to the n belongs to this coset. That means alpha 1 to the n is alpha 2 to the n times something inside f raised to power n. So that's something inside f, let's call it c. So for some c inside f cross, alpha 1 to the n is supposed to be the other coset representative times something inside f raised to power n. Okay, and let's call this guy to be a, and that we know is inside f. So both alpha 1 and alpha 2c are zeros of x to the n minus a. So both alpha 1 and c times alpha 2 are zeros of x to the n minus a. By this argument that we had earlier, that means that one of the zeros is the other one times a power of zeta. But notice c is inside f, zeta is inside f. That means that alpha 1 is alpha 2 up to a multiple inside f. Okay, what does that mean? This means when I apply sigma to alpha 1 and divide out by alpha 1, what do I get? It's like applying sigma
to this element of f times alpha 2 divided by this element of f times alpha 2. Now sigma is f linear. So I can take out this f linear f part. So I get this f part times sigma of alpha 2 divided by the f part times alpha 2. These guys cancel out. We end up getting that it's the same as sigma of alpha 2 divided by alpha 2. This shows that f is well defined. So we defined a function that takes an f linear automorphism of E and some element inside delta of E, and it gives us an nth root of unity. Now, next thing that we want to show is that this function f is nice in the sense that with respect to each one of the components separately, it's a group homomorphism. So with respect to if I fix an element inside delta E and just change sigmas, it's going to be a group homomorphism in terms of the sigma component. If I fix sigma and change the element inside delta E, it's going to be a group homomorphism with respect to these elements of delta E. So that's the claim. So f is a group homomorphism with respect to each one of the components separately. Okay, so we need to show that it's a group homomorphism with respect to the first component. Then we need to show that it's a group homomorphism with respect to the second component. Let's start with the first component. So I pick two elements in f linear automorphisms of E, and I fix the second component, and let's say the alpha to the n, the coset that's represented by alpha to the n is the fixed second component. Okay, so let's apply this pairing to the pair sigma 1 and this element in delta E. And suppose that I end up getting this nth root of unity zeta to power I1. I do the same for sigma 2 and the same element inside delta of E, and assume that I end up getting zeta to power I sub 2. What we need to show is that when I look at the pairing of sigma 1 composed with sigma 2 and the same element in delta of E, I get the product of zeta to power I1 and zeta to power I2. So the claim is that f of sigma 1 over sigma 2 and the same coset is going to be zeta raised to power I sub 1 plus I sub 2. That is what we need to show. Now, what does this mean? This means that sigma 1 applied to alpha divided by alpha is this, which means sigma 1 of alpha is zeta to power I sub 1 times alpha. Similarly, this equality means that sigma 2 applied to alpha is zeta to power I sub 2 times alpha. Now, when I look at the composite of sigma 1 and sigma 2 applied to alpha, we end up getting that it's sigma 1. Okay, so sigma 2 of alpha is this, so we put it in. Zeta belongs to the base field, and sigma 1 is f linear. So I can take out zeta, so I get the zeta raised to power I sub 1 times sigma 1 of alpha. Sigma 1 of alpha is zeta to power I sub 1 times alpha. So altogether, we get exactly what we wanted. So this means that this fraction is zeta to power I sub 1 plus I sub 2, and that's exactly the quantity that this pairing gives us. So with respect to the first component, we showed that it's a group homomorphism. Now let's focus on the second component. This means that I'm fixing an f linear automorphism of E, let's call it sigma, and then I give you two cosets, one of them represented by alpha 1 raised to power n, and the other one is represented by alpha 2 raised to power n. Let's assume that when I pair sigma with the first coset, I get zeta to power I sub 1, and when I pair sigma with the second coset, I get zeta to power I sub 2. Now I need to show that when I pair sigma by the product of these cosets, I end up getting zeta to power I sub 1 plus I sub 2. This is what I need to show. But again, what does that mean? The first pairing implies that when I apply sigma to alpha 1, it's zeta raised to power I sub 1 times alpha 1. When I apply to alpha 2, it's zeta raised to power I sub 2 times alpha 2. Now I need to understand what sigma does to alpha 1 times alpha 2. So sigma is an automorphism. Sigma of alpha 1, alpha 2 is sigma of alpha 1 times sigma of alpha 2. And that's now rather easy. We end up getting these equalities, and that means that sigma of alpha 1, alpha 2 divided by alpha 1, alpha 2 is zeta to power I sub 1 plus I sub 2, and that's exactly what we needed to show. So we end up getting this pairing, and we end up showing that with respect to each one of the components, this is indeed a group homomorphism. It seems very interesting, very strong result, but notice that, okay, so in order to understand it a bit better, we can focus on one of the components a bit better. I mean, so let's think about it like this, that I'm going to fix my sigma and then ask myself, what does this pairing give me? Fixing sigma, or maybe the other way around. So I fix alpha bar, I fix alpha and alpha bar inside the second component. Then what do I get? Given sigma, I end up getting a group homomorphism. So given sigma, if I look at f of sigma alpha bar, with respect to this first component, I'm getting a group homomorphism. So this means that for every alpha bar, if I fix it, this function, this pairing, gives me a group homomorphism from F linear automorphisms of E to the group of units. You see, a group homomorphism from any group to an abelian group always factors through the largest abelian quotient of this. What do I mean by that? So I mean that if I take a map that goes to an abelian group, then every element of the form sigma O sigma prime O sigma inverse O sigma prime inverse goes to identity, goes to 1. So these elements we get no information about these type of elements through these type of group homomorphisms to abelian quotients. And at the same time, m sub n is n cyclic. This means that we get no information. So every element inside this guy raised to power n, when I apply this map, goes to identity. So again, those type of elements we get no information about. So we get only information about abelian quotients of this that have exponent n. That means that when I raise them to power n, I get identity. That's the only possible expectation that we can have. Okay, have this in mind. We'll come back to this later. So far, we are saying that for fixed alpha bar, we get a function from F linear automorphisms of E to M sub n, and this is a group homomorphism. So F sub alpha bar of sigma is the pairing that we are getting, and this is a group homomorphism. Therefore, we get a function from the second component to the set of group homomorphisms from the first component to the group of units. And what is this? Given alpha bar, it spills out this group homomorphism F sub alpha bar. I can do the same for the second component, and I can define F sub sigma to be the group homomorphism that we get from delta of E to M sub n. We'll do that later, but for now, let's introduce only these two notation. So remember, again, F sub alpha bar means I'm fixing the second component, then I get a group homomorphism from the first components to the group of units. And that means for a given second component, I end up getting a group homomorphism from the first components to M sub n. So that's how we are defining this f hat and f sub alpha bar. Yeah, we will also later introduce f sub sigma. Okay, now we have enough tools in general settings. Now let's go back to the cyclic case and try to see how this pairing can help us to prove Coomer's theorem for the cyclic case of Coomer theory. Okay, so that means what? That means we need to start with showing why the functions lambda and delta that we had are in fact well-defined functions. Let me go back to the statement of the theorem for you guys to be able to see these lambda and delta. Lambda starting with a cyclic group that's generated by a coset that's represented by A spills out the field that's generated by a solution of x to the n minus the coset representative joined with F. And delta takes an intermediate subfield, raise all the elements to power n, asks which one of these guys are inside the base field, and then looks at the quotient of that guy by F cross to the n. So here we need to show why it's independent of the choice of coset representative. Why, so over here, and why is it independent of choice of a generator for the cyclic group, and why is it independent of choice of a 0 of x to the n minus a. So these are the three issues that we have to address over here. Over here, we need to address why this is a cyclic group. Then we have to show why lambda and delta are inverse of each other. And finally, we need to show these isomorphism. Okay, so let's start the argument. So again, recall that lambda of the cyclic group is f joined with the nth root of a. We have already proved this part, that this is indeed a splitting field of x to the n minus a, and so it doesn't depend on the choice of a 0 of x to the n minus a. It does not depend on this choice of the nth root of a. This part is okay. And also it's a normal extension, its characteristic is 0, it's a Galois extension. We have also proved that the Galva group is a cyclic group. In fact, the way that we showed it was like this, that we chose alpha 1 to be this coset, and we essentially looked at f sub alpha bar from F linear automorphisms of this Galva extension to the group of units. Remember, we did not use the notation f sub alpha bar, but we did use this function. We applied sigma to the nth root of a and divided out. This is alpha. Alpha is the nth root of a. This is a 0 of x to the n minus a. And then alpha bar would be alpha raised to power n, which is a, f cross to the n. So it's exactly f sub alpha bar. And then we looked at this quotient. We showed that this is, okay, now I can repeat this. So if I call alpha bar to be this guy, then f sub alpha bar would be f sub alpha bar of sigma, by definition, is f of sigma, this pairing, and that is this quotient. We've proved that f sub alpha bar is a group homomorphism. Now, if I show that this group homomorphism is injective, as we did before, but I'm recalling the proof, we deduce that this extension is indeed a cyclic extension, and the cardinality of the group or extension divides n. It can be embedded into z sub n. So suppose that sigma is in the kernel of f sub alpha bar. What does that mean?
This means that this quantity is 1. Sigma of the nth root of A is the nth root of A. Sigma is an F linear map from F joined with nth root of A. It sends nth root of A to itself. It's identity over here, so it is identity. That means that the kernel of F sub alpha 1 is 1, is trivial, and that means F sub alpha 1 is injective, and that shows that the extension that we are getting is indeed a cyclic extension that can be embedded into Z sub n. Okay, so at least it is inside the target image. I still need to argue why, if I choose different A, I end up getting the same intermediate subfield. This I will show later. But now let's look at why the other side, why delta gives me a cyclic extension. So suppose I give you an extension, intermediate extension, that is a cyclic extension, and the group of automorphisms can be embedded into Z sub n. So this is a cyclic extension, and its cardinality, its order, divides n. Now F has an element that has order n. We have proved that whenever we have such a thing, we used Hilbert's theorem 90 to show this statement. We looked at the norm of this zeta because it has order n, and n is divisible by n. So we looked at zeta to power something in order to make it precisely the order of the field extension, and that belongs to the base field. Then we looked at norm of this element, it's 1. One can use Hilbert's theorem 90 and find out what this nth root of A is. We use this to show that an extension of this type is a Coomer extension. So it is definitely of the form F joined with nth root of A for some A inside F cross. Now, we want to show that this delta E is a cyclic group. What we will do, we show that this can be embedded into cyclic group of order n, from which we can deduce that it's a cyclic group, because every subgroup of a cyclic group is cyclic. Now, what is our assumption? The assumption is that the set of F linear automorphisms of E is cyclic. The group of F linear automorphisms of E is cyclic. Suppose that it's generated by sigma naught for some sigma naught. Now again, we use Coomer pairing. And this time I'm going to fix the first component and get a group homomorphism from the second component to the group of units. Let's denote this by F sub sigma naught. So F sub sigma naught sends a coset to the pairing of sigma naught and that coset. And we show that when we fix the first component with respect to the second component, we get a group homomorphism. So F sub sigma naught is a group homomorphism from delta of E to M sub n. So it's a group homomorphism. Next, we are going to claim that this group homomorphism is injective. So suppose that some coset is in the kernel. So suppose alpha bar is in the kernel. That means what? That means sigma naught fixes alpha, because this is quotient of sigma naught of alpha by alpha. So it's sigma naught of alpha is alpha. What does that mean? So what is alpha? Alpha is the element inside E that gives me this coset. Now, alpha is in the fixed points of sigma, and therefore it's a fixed point in the cyclic group generated by sigma. The cyclic group generated by sigma is the entire F linear automorphisms of E. So the set of fixed points of this Galois extension, the group of F linear automorphisms of this Galois extension, is the base field. That means alpha does belong to the base field. So alpha is inside the base field. See again, this is equal to this this extension is Galois, so alpha is in the base field. That means alpha bar is trivial because that means alpha to the n is in f cross to the n. So I'm getting the trivial element inside this quotient. So f sub sigma is injective. F sub sigma is injective. That means that delta of E can be embedded into a cyclic group of order n. So it is a cyclic group. Okay, so we haven't quite showed that lambda is well defined, but I'm going to do it at the same time. So if I show that delta O lambda is identity, so again, I haven't shown that this is a well-defined function, but if I show that delta of this field is the cyclic group, then if I choose a different coset representative, I'm going to get the same thing as before, because I can apply the same. So if I choose a different coset representative, I end up getting the same field. And then I'm going to get same. Okay, then let me justify this before. Maybe it's better to make it clear why lambda is well defined before we get to the composite. It was better to write it down before this, but let's include it. Yeah. So maybe it's better to include it over here. So if I tell you that if I give you two different coset representatives, so A1 is the same as F2, A2. So that means A1 is C to the n A2. Now I take the nth roots of both sides. I've written this later on, but let me go over this. So then both of these guys are roots of x to the n minus this A1. So for some roots of unity, I end up getting this equality. Now when I add this guy to the base field, it's like adding this guy to the base field. But remember, this is already inside F. So it's like adding this guy to the base field. So we get that we are getting the same fields after adding the nth root of A1 or the nth root of A2. We end up getting the same field. This is why lambda is well defined. I mean, I'm going to repeat this argument later, but for now, I wanted to make sure that we also know why lambda is completely well defined. Let's discuss why composite of delta and lambda is identity. What does that mean? This means I want to show why this field raised to power n intersected with f cross when I mod out by f cross to the n is the cyclic group generated by A. You see here, I don't need to say why lambda is well defined. I want to show this equality. But I mean, I've also discussed it, why it is well defined, but let's see why this equality holds. What is clear is that this is a subset, a subgroup of this side. Why is that the case? Because nth root of A raised to power n is inside f cross, and that is A. So I do have this coset inside this group. And that means that this inclusion is clear. Okay, so A does belong to this intersection, and therefore this coset does belong to this quotient, and that means that the right-hand side contains the left-hand side. Now I want to show the other way around. So suppose, what does the other way around mean? It means that I have to pick some element over here, and I have to argue that the coset that I'm going to get is going to be in the group generated by A. So I'll continue the proof of Coomer's theorem for cyclic extensions in the next lecture.